Hello, this is question 16 in your June 2022 Pure Paper 2 from edexcel. You have a curve in parametric equations, so this one. They give you the equations and the limits of the parameter, and they say the line L is normal to C at the point P with this parameter. So this line is normal, perpendicular to the curve here at this point. And we have to show that this equation using parametric differentiation is this one. So we need to find the equation of this line. Remember, when we find the equation of the normal to a curve, what we can do is to find the gradient of the tangent, and with that find the gradient to the normal. And to find the gradient to the tangent, I'm just going to differentiate. To differentiate parametric equations, so if I want to find dy by dt, what I'm going to do is differentiate with respect to the parameter. So I'm going to differentiate y, and I'm going to differentiate t. Y is this function here, is sec squared. When I differentiate with respect to t, derivative of sec is sec tan. So let me show you the formula booklet. This is in the formula booklet, so you don't have to remember. The derivative of sec is sec tan. So in this case, I have is a square, so I'm going to multiply my whole function by 2. So I'm going to have this 2, another 2, and then sec with 1 degree less, and sec tan. So I derivate using the chain rule, and I have my 2 times 2 because of the square, sec to 1 degree less, and then the derivative of sec, which is sec tan. Yeah, and so this is the numerator because the other term is not giving us any differentiation. And when I'm going to derivate the denominator, I have the derivative of tan, and remember, derivative of tan is sec squared. Again, it's in your formula booklet. So derivative of tan is sec squared. So this is going to be 2 sec squared, and this is not giving me anything. So this all is going to be divided by 2 sec squared t. And I can simplify. So I can simplify this 2 with 1, 2, and this sec with this sec squared. So my derivative, my function, my gradient function really is 2 tan t. And this is going to give me the gradient of the tangent in any point. I need the gradient of the tangent when at P. And P, we say P is when the parameter is pi quarters, I think. Yeah, P is when the parameter is pi quarters. So I just have to substitute here to find the gradient. The gradient of the tangent, I'm going to write T, so you remember. The gradient of the tangent is 2 times tan of pi quarters. You have to be sure the calculator is in radians, yeah? And this is 2, because tan of pi quarter is 1. You will remember that. So this is the gradient of the tangent, which means the gradient of the normal is going to be reciprocal and negative, so minus 1/2. To have the line, the equation of the line, I need the point, the coordinates of the point. I know the parameter, but I don't know the x and y coordinates. So my x coordinate is going to be this function here when t is pi quarters. So I have 2 tan of pi quarters, we say is 1, so 2 times 1 plus 1, or I can write the whole thing if you want. So 2 tan of pi quarters plus 1, and this is 3, we say. Yeah, and y is going to be 2 sec square of t plus 3, so 2 sec square of pi quarters plus, we say plus 3? Plus 3. Sec of pi quarters is not in the calculator, so remember, sec is the reciprocal of cos. So I have to do 1 over cos of pi quarters, which is 1 over root 2, which means sec is root 2, and sec square is going to be 2. Sec square of pi quarters, not t, pi quarters, is going to be square of that, which is 2. So here I have 2 times 2 which is 4, plus 3, 7. So my point P is the point of coordinates 3, 7, which means my line, so L, is going to be y minus the y of the point is the gradient, brackets, x minus the x of the point. Remember, I just substitute what I know. So y minus 7 is going to be my gradient, which is minus 1/2, x minus 3. And I rearrange this until it looks what it has to look, which is this thing here. Yeah, so it's just that. I'm going to expand the bracket and move the 7 to the other side. So I have y is minus 1/2 x, and then I have positive 3/2 plus 7 is 17/2. And this is the equation that I have to find. Yeah, this one. So this is A. Then B says, show that the points, all points on C satisfy this equation. So they have eliminated the parameter. This is the Cartesian equation. So what I have to do is something to eliminate the parameter between x and y. So I'm going to copy both equations here. I should have done before. So x is 2 tan t plus 1, and y was 2 sec squared, I think, plus 3. Plus 3. So these are my two equations, and I need to eliminate t between both of them. So I have tan here and I have sec here. There are maybe more ways of doing it, but my first attempt could be with the identity that you know that relates sec and tan. So remember that 1 plus tan square is going to be sec square. We have sec square. If we make tan the subject and square it, we will have an expression for tan x squared. So from 1, tan t is going to be x minus 1 divided by 2. And for the second one, I can have sec square is y minus 3 divided by 2. If I substitute all this in my here, right, in my identity, I have 1 plus tan square is going to be x minus 1 squared divided by 4 is going to be sec square, which is y minus, I don't have to square it because it's already squared. If I rearrange this, I can multiply everything by 2, and I have 2 plus x minus 1 squared divided by 2 is y minus 3. I write the 3 in the other side, and I have what I need to have. So x minus 1 squared divided by 2 plus 5, which is what I have to find. Yeah, you see the expression here. I don't even have to expand the bracket. And then the next thing they say is the straight line with equation, this one, and you can compare this one with the normal. So it has the same gradient, it's just parallel to the normal line, and intersects C at two distinct points. Find the range of possible values for K. So if you go to your sketch, we are talking about a parallel line to this line here. Yeah, parallel line, because it has the same gradient. So it could be anything like this. The line is going to intersect my curve C in 2 points. If it's below, I'm not going to do it very well, but I'm trying to do parallel to that one. So if it should be a bit down, yeah. Let's say this is a tiny bit higher. So this line is the first one that intersects the curve in 2 points. Anything above this is going to cut only in ones. So my line is going to be between this one and this one. So these are the two lines that intersect. This one is not, the last one is going to intersect in just 1 point if it's tangent. Above this one and up to this one, they are all cutting in 2 points. Yeah, so I'm looking what K is here. I need the K here, and I need the K here. Yeah, this is tangent. So the intersection between this line and the curve is going to have one real solution. It's going to touch in just 1 point, and I can do that using the discriminant. So I'm going to find the intersection between that line, so this one, and this curve and make it to have only one point of intersection. So let's going to do that, and I'm going to do it the next page. So for C, I'm going to force my line, which is y is minus 1/2 x plus k, and the curve that was in parametric equations x minus 1 squared divided by 2 plus 5 to have one single solution, one double solution. So I can make both equal, and I have x minus 1 squared divided by 2 plus 5 minus 1/2 x plus k. I rearrange expanding bracket, and I have, and I'm not going to do it to not take a lot of time, I have this x squared minus x plus 11 minus 2k is 0. So this equation is going to have one solution when my discriminant is 0. So my discriminant is b squared minus 4ac, remember? And this is going to be 1 minus 4 times a is 1 and c is 11 minus 2k. And this is 0 when k is 43/8. And this is when the line is, let me show you. This is this value of k. So when the line is touching in one point, so it's tangent to the curve. What we are going to find is this k here. And this k is when the line passes this point. This point is the point of the curve when t is minus pi fourths. Yeah, so we find x and y when when t is minus pi fourths to find this point here. To do that, you just substitute t by minus pi fourths. So we have 2 terms of minus pi fourths plus 1, and this point is minus 1, and then I substitute y, which is 2 sec square of minus pi quarters plus 3, and this is 7. So this point here is the minus 1, 7. Yeah, so I know this point, so, and I know the gradient of this line, so I can write that line is going to be passing the point minus 1, 7, and my line is y is minus 1/2 of x plus k. It has to pass the points minus 1, 7, so I substitute this minus 1, 7, and I find k. Yeah, and k is going to be 13/2. When so I can give the limits for my k. My k must be greater than 43/8, which is this point here, and it's going to be greater. It cannot be equal, because if it's equal, they are the intersection is just 1 point, not 2. But the other one is going to be equal, because when my line passes this point, it cuts still into points. So my other k is going to be with the equal 13/2. So these are the limits for k, and they come from that. So the intersection between a line and a curve, and the quadratic and the discriminant. And that's it. That's find the range of possible values for k. That's the last thing they ask. Yeah, that's all.